Let us talk about exponential distribution. So let x be a continuous, random variable. Exponential variable random variable basically model the time until an event happens. Assuming that the event of our interest happens randomly and continuously. Randomly and continuously over time. So let us officially define this. A continuous random variable whose probability density function is given as f of x to be equal to, if x is more than equal to 0, it follows an exponential function lambda e to power negative lambda x, and when x is less than 0, it is 0. Lambda is just a positive number. So if your continuous random variable has probability density function as follow, it's said to be an exponential random variable. We already have parameter lambda, so we're going to add it here with parameter lambda. We can calculate the cumulative distribution function f as follow. The cumulative distribution function or f is calculated as f of a is equal to the integral of lambda e to power negative lambda x dx, while x ranges between 0 to a, and a is more than equal to 0. So basically, you can just write a here, and then later on take the limit if you want to, and a is more than or equal to 0. Let's go back to calculus. F of a is equal to, so basically, since we are taking the integral with respect to x, we can use u sub. Let u to be negative lambda x, du is negative lambda dx. So basically, this guy is equal to 1 minus e to power negative lambda a, and a, as we mentioned, is more than equal to 0. And please note that if you take the limit as a goes to infinity, f of infinity is equal to 1 minus 0, which is basically 1, or you get the integral 0 to infinity of lambda e to power negative lambda x dx, which is nothing but 1. Suppose we're interested in calculating the expected value of exponential random variable. What is the expected value of an exponential random variable? So remember the formula to find the expected value. You have the expected value to be the integral of x times the function lambda e to power negative lambda x dx, and your x ranges between 0 to infinity. We need to apply integration by parts. Integration by parts. So assume u is equal to x and dv is equal to e to power negative lambda x. We can put lambda next to it to make it a little bit easier. Dx, so du is equal to dx, and v is equal to negative e to power negative lambda x. So this integral becomes e of x to be uv x times negative 1 divided by e to power lambda x, and remember lambda is positive, minus the integral v du. V is negative, e to power negative. Let me use the same color. Negative e to power negative lambda x, and here you have your dx. Okay, and this guy goes from 0 to infinity, and here you have 0 to infinity. So of course, if you plug in infinity, this goes to 0, and if it's 0, you get your 0 back. So here you e of x so far is equal to 0 minus 0, which is just basically 0, minus the integral, or here you have plus the integral 0 to infinity of e to power negative lambda x dx that we calculated before. This is very similar to what we did before, so nothing new. E of x is equal to 1 divided by lambda. So this is just the expected value of an exponential random variable. Again, if you want to see more detail, here you have u negative lambda x, and du is equal to negative lambda dx. This becomes the integral of e to power negative lambda x, or e to power negative u, and your dx is equal to du divided by negative lambda. So you already know how to calculate this. Let us avoid writing this in more detail. Let's go over a quick example together. In this example, you have the following case. Suppose that an electric system has a certain type of components with time in years to failure is denoted by T. The random variable T, we already know that is an exponential random variable. Is an exponential random variable with mean time to failure to be 5. The question is, if 5 of those components are installed in different systems, what is the probability that at least 2 of them are still functioning at the end of 8 years? So remember that to calculate the probability that t is more than 8 years can be calculated as, since an exponential distribution, we're going to follow the exponential function here. So let me just copy this guy down for you. And put it down here. This is equal to, here you have your lambda. Your lambda is equal to 1 divided by 5, because the time to failure is 5. This is your mean time to failure. So it means that you end up with 1 over 5. The integral 8 to infinity of e to power negative 1 over 5 of t dt. So basically, we're just doing the calculation. Here you have, if u is equal to negative 1 over 5t, du is negative 1 over 5 dt. So you already have 1 over 5. You're going to just multiply by negative sign, and you end up with negative e to power negative 1 over 5t, 8 to infinity. So if you plug in infinity, this is basically just 0. So you have e to power negative 8 over 5. If you use your calculator, this is approximately 20%. So you get approximately 20%. So the probability that a given component is still working after 8 years is about 20%.